So when we discuss the classical problems in process synchronization, one of the classical problems we can consider as this dining philosophers problem. So what is this dining philosophers? So here the demonstration and the concept behind this dining philosophers problem is that the different processors will be using different number of limited resources to complete the processes. So the operating system is dedicated for processing, and how it handles these processes are when a particular process is ready to execute. First, it will check whether there are necessary resources for that particular process to start its execution. And then when the process starts, the resources will be allocated for that particular process. So then after a while, that process will complete. So immediately after the process completion, the given resources will be released, and the resources can be used by another process or set of processes. So that is the basic fundamental operations. So here also the philosophers uh, are like processors, because they will think and they will eat. So those are the two different activities that the philosophers has. So you can see their lives are very much limited. So they think or they eat. So when they think, it's like a process in idle, right? So when the process is idle, that process will do nothing, right? So when the philosophers think, they don't do anything, they don't need anything, so they will think. But when they get hungry, they will try to eat. So it is like a process is ready for execution. So when the philosophers get hungry, they need to eat. So in the given table, it is a circular table. So there are 5 chopsticks. So there are 5 philosophers and 5 chopsticks. Each chopstick is between 2 philosophers. So later on, I will show you the diagram. So there are 5 philosophers sitting in a circular table, and there are 5 chopsticks. So each chopstick will be between 2 philosophers. So when the philosopher gets hungry, then the philosopher should get hold of the left and right chopsticks. Then he can eat. So that is the way that the philosopher will eat. So here, this left and right chopsticks are the resources. So when the resources are available, that process can start functioning or start execution. So the philosopher, when 2 chopsticks are available, then the philosopher can eat. So remember, when a philosopher needs to eat, that philosopher has to obtain both left and right chopsticks. He cannot eat with 1 chopstick. So therefore, the philosophers uh, processes are thinking and eating. Thinking is like process being idle. Eating means a process being executed. So when a process needs execution, it requires resources. So the resources are allocated for uh, to start the process execution. So immediately after process completes, it will release the resources. Same thing here. When a philosopher complete its eating task, he will release both left and right chopsticks. So another philosopher who gets hungry can get hold of the left and right again and start eating. So, so how many philosophers can eat in this situation at any given time? What is the maximum number? it will be 2, isn't it? Because there are 5 chopsticks and 5 philosophers, right? So can two neighboring philosophers eat together? They can't, right? Why? Because they cannot share a chopstick, right? So one philosopher needs to get hold of both left and right chopsticks to eat. So we can show the situation in these two diagrams. So these are the grumpy old philosophers, as you can see. So they will think or they will eat. So here it is forks indicated, but normally in the classic problem, we call it as chopsticks. So you can see there are different notations given to demonstrate the same thing, same concept. So it is to show that the operating systems has large number of processors, but limited number of resources. So the round table is like the operating system. So it will allocate resources when it is available and when it is required for the necessary processes. So the bowl of rice is like the data, right? Because it has the necessary food for them. So they will put the food into their plates and start eating by using the chopsticks. So so this is the operation. They will uh, think for a while, and when they get hungry, they will pick up the chopsticks and they will eat for a while. When their tummy is filled, they will put down the chopsticks and start thinking again. So those are the two operations that we need to think in dining philosophers problem. So the limitations here is that when each and every philosopher gets hungry at the same time, and if they are holding to the left hand side first and then to the right hand side, everyone will hold one chopstick and wait for the other chopstick to be released. What happens in this situation? Then it's a deadlock situation. Why? Because all of them gets hungry at the same time and start holding the chopstick to the left first, then to the right. So everyone will hold to the chopstick to the left immediately, then search for the right hand side. But at that time, the right hand side chopstick is already acquired. So operating systems are also like that. Sometimes the limited resources will get held by different processors and they need more resources, but they don't release the existing more. The resources are being held already. So same situation here. The problem is this can create a deadlock if it is not properly handled. Right. So the ideal situation is when two philosophers get hungry and those two will get the chance to eat, as you can see in the right hand side uh, figure. So two philosophers get hold of the two chopsticks and start eating. So here you can see some of the codes, right? So to check whether a philosopher can eat, they need to check whether the chopstick to the right and the chopstick to the left both are free. So it will check both. Wait, chopstick is in the array. So it will check for both I and I plus 1. I is to the left, I plus 1 is to the right. So if both are not being used, that philosopher can take both and eat. Immediately after eating, it will put back the chopsticks back again. So this is another application of semaphores. So you can see the semaphores are used here. So it is an array, right? So each element of the array will consider as a part of the semaphore. So either it will be 0 or 1. When it is used, it becomes 0. When it is free, it is initiated to 1. So a simple solution can be implemented using semaphore for a philosopher for eating and thinking. So there's another set of codes that I will not explain in this particular instance about dying philosophers. So you may refer to the textbook and see how the full coding is implemented and executed properly for uh, as a solution for dining philosophers.